Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin our journey together, take a moment to get comfortable wherever you are. Adjust your pillow, pull that blanket a little closer. Let your body settle into the surface beneath you. Where in the world are you watching from? Perhaps you're in a quiet bedroom with the lights dimmed low. Or maybe you're in a cozy corner where the day is finally winding down and the night feels gentle and safe. Tonight we're going to explore one of the most intriguing mysteries in modern astronomy, a signal from deep space that reaches Earth with clockwork precision every 44 minutes. We'll discover what radio telescopes have detected, understand how astronomers work to identify these cosmic broadcasts, and contemplate what it might mean when the universe sends us messages we can't quite decipher. It's a journey that spans billions of light years and touches on some of the deepest questions we can ask about what else might be out there in the darkness. But don't worry. This isn't going to be a dramatic hunt for aliens or a sensational mystery designed to keep you on edge. Instead, we'll move slowly and carefully through the science, the observations, the possibilities, taking our time with each discovery and each question. By the end, I think you'll find a kind of peace in the cosmic puzzle, a quiet wonder at the universe's ability to surprise us. If you enjoy these calm explorations of space and the cosmos, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for trusting these journeys into the night sky. So settle in now. Let your shoulders drop away from your ears. Take a slow, deep breath and release it gradually. And let's begin our slow drift through this cosmic mystery. There's nowhere you need to be right now. Nothing you need to do. Just listen and let the story of this remarkable signal unfold across the darkness between stars. In the summer of 2022, a team of astronomers in Australia noticed something unusual in their data. They weren't looking for it specifically, which is often how the most interesting discoveries happen in science. The researchers were using the Murchison Wide Field Array, a radio telescope in Western Australia's remote outback, designed to peer deep into space by listening to radio waves that travel across cosmic distances. On a routine survey of the sky, mapping radio sources as they do on countless ordinary nights, the computer flagged something peculiar. A repeating signal with a precision that seemed almost impossible. Every 44 minutes, give or take just a few seconds, a burst of radio energy would arrive at Earth from the same point in space. Not approximately every 44 minutes, not roughly that interval, but with a regularity that would put many atomic clocks to shame. In a universe filled with chaos and randomness, with explosions and collisions and the messy violence of stellar death, here was something that seemed to tick like a metronome, patient and precise across unimaginable distance. The source wasn't bright in the traditional sense. You couldn't see it with your eyes, couldn't photograph it with an optical telescope pointed at that patch of sky. It existed only in the radio spectrum, in frequencies our bodies can't perceive but our instruments can detect and measure with exquisite sensitivity. When it pulsed, it sent out waves of radio energy that had travelled for an unknown span of time across the galaxy, perhaps longer, before washing over our planet like invisible tides. What made this signal particularly fascinating was its constancy. The universe is full of radio sources, from distant galaxies with active black holes at their centres to closer objects like pulsars, the rapidly spinning corpses of dead stars. But most of these follow patterns we understand, rhythms that match what we expect from known astrophysical processes. This signal, catalogued with the designation GLEAM-X J162759.5-523504.3, a name that captures its position in the sky with mathematical precision, didn't quite fit the existing categories. The research team, led by Dr. Natasha Hurley-Walker from the Curtin University node of the International Centre for Radio Astronomy Research, began the careful work of characterization. They measured the signal's brightness, its duration, the exact timing between pulses. They looked for patterns within patterns, variations that might give clues to the source's nature. They cross-referenced it with other surveys, checking if anyone else had spotted this cosmic timekeeper in different frequencies or at different times. What they found was both illuminating and puzzling. The signal would pulse for between 30 and 60 seconds during each 44-minute cycle, sending out radio waves before falling silent again. During its active phase, it was remarkably bright in radio terms, one of the most luminous sources in that region of sky. Then it would vanish completely, leaving no trace until precisely 44 minutes later, when it would begin again, faithful as sunrise but far more mysterious. And this brings us to something equally remarkable, the realization that this signal had likely been calling out to us for years, perhaps decades or longer. And we'd simply never noticed until that moment in 2022, when the right telescope was looking at the right patch of sky with the right sensitivity to detect its persistent cosmic rhythm. To understand what makes this signal so intriguing, we need to contemplate what radio waves actually are and how we use them to listen to the universe. Radio waves are a form of light, though not the kind our eyes can see. They exist on the same electromagnetic spectrum as visible light, alongside infrared warmth and ultraviolet glow, X-rays and gamma rays, all different expressions of the same fundamental phenomenon, electromagnetic radiation propagating through space. Radio waves have the longest wavelengths in this spectrum, which means they can pass through dust clouds that would block visible light completely. This makes radio astronomy particularly valuable for peering into regions of space where optical telescopes see nothing but darkness. A star-forming nebula thick with gas and debris appears opaque to traditional telescopes, but radio waves slip through as if the obscuring material wasn't even there, revealing the hidden processes of stellar birth. The radio universe is also, in many ways, a different universe than the one we see with our eyes. Objects that appear bright in visible light might be radio quiet, barely whispering at these longer wavelengths. Conversely, sources invisible to optical telescopes can be screaming loud in radio frequencies, dominated by physical processes that don't produce much visible light, but generate powerful radio emissions. Supermassive black holes at the centres of distant galaxies, for instance, can launch jets of particles and magnetic fields that shine brilliantly in radio wavelengths, while remaining relatively dim optically. When we build radio telescopes, we're essentially constructing enormous ears for listening to these cosmic broadcasts. The Murchison Wide Field Array that detected our mysterious signal consists of thousands of individual antennas spread across the Australian outback, working together as a single instrument with a collecting area equivalent to a football field. These antennas detect the faint radio waves washing over Earth from cosmic sources, converting them into electrical signals that computers can process and analyse. The signal arriving every 44 minutes travels at the speed of light, the universal speed limit that governs all electromagnetic radiation. Depending on how far away the source is located, the radio waves we detect today might have begun their journey decades, centuries, or even millennia ago. The light from our sun takes 8 minutes to reach Earth, so when we look at the sun, we see it as it was 8 minutes in the past. The nearest star system, Alpha Centauri, appears to us as it was just over 4 years ago. The radio signal we're discussing could have originated from a source dozens or hundreds or thousands of light years distant, meaning we're observing events from the ancient past. But radio waves, unlike visible light, can carry information in their structure beyond just brightness and position. Astronomers analyse the polarization of radio waves, the way the electric and magnetic fields oscillate, which provides clues about magnetic fields at the source. They examine the spectrum, how the intensity varies across different frequencies, revealing the physical processes generating the emission. They measure any Doppler shift, the stretching or compression of wavelengths caused by motion toward or away from us, which tells us about velocity and cosmic expansion. The 44-minute signal exhibits characteristics that mark it as something genuinely unusual. Its radio spectrum is broad, emitting across a wide range of frequencies rather than at a single pure tone. This suggests a complex source, not something simple like a single, rotating object with a hotspot. The polarization indicates the presence of strong magnetic fields, twisted and organized in ways that require substantial energy to maintain. The brightness variations within each pulse hint at structure and dynamics, processes unfolding on timescales of seconds, even as the larger 44-minute rhythm continues unchanged. Which leads us naturally to consider the fundamental question that drives all astronomical investigation. If we can characterize how something appears, what does that tell us about what it actually is? When astronomers discover a new type of signal from space, they begin a methodical process of elimination, comparing the observed characteristics against a catalogue of known cosmic phenomena. It's detective work conducted across light years, using physics and mathematics as the tools of investigation. For our 44-minute signal, this process revealed just how unusual the discovery truly was. The first obvious candidate to consider was a pulsar, those remarkable objects that have fascinated astronomers since their discovery in 1967. Pulsars are neutron stars, the collapsed cores of massive stars that exploded as supernovae, compressed to such extreme density that a teaspoon of their material would weigh billions of tons. These objects spin rapidly, sometimes hundreds of times per second, and their powerful magnetic fields channel radiation into beams that sweep across space like a lighthouse beacon. When one of these beams happens to point toward Earth during each rotation, we detect a pulse, hence the name pulsar. The thing is, pulsars pulse fast. Most rotate multiple times per second, with periods measured in milliseconds to seconds, occasionally stretching to a few seconds for the slowest known examples. The physics of neutron stars makes it extraordinarily difficult for them to maintain stable rotation at periods much longer than about 10 seconds. Their immense gravitational fields and fierce magnetic pressures create forces that tend to either speed up or break down slower rotation patterns. A neutron star pulsing every 44 minutes would be violating what we thought we knew about these objects. Some pulsars do show intermittent behaviour, switching on and off over timescales of minutes to hours, but the on-off pattern is irregular and doesn't maintain precise periodicity over long durations. Our signal's clockwork precision over repeated observations argued against this explanation. It wasn't flickering randomly, it was ticking with purpose, driven by whatever physical mechanism created it. The next possibility to explore was a type of object called a magnetar, a neutron star with magnetic fields taken to an even more extreme level. Magnetars possess the strongest magnetic fields known in the universe, quadrillions of times stronger than Earth's protective magnetic bubble. These fields are so intense they can literally warp the structure of space itself in the immediate vicinity of the star. Magnetars are known to produce bursts of X-rays and gamma rays, sudden releases of magnetic energy that brighten them dramatically for brief periods. Some magnetars have been observed to emit radio waves as well, though this behaviour is less common and not fully understood. The extremely strong magnetic fields could potentially create emission patterns we haven't seen before, driven by processes at the edge of physics as we know it. Could a magnetar somehow produce the observed 44-minute periodicity? It seemed possible, though it would require a configuration or behaviour not yet documented in the dozens of known magnetar systems. Researchers also considered whether the signal might come from two objects in a binary system, orbiting each other and creating periodic changes in their observed properties. Many stars exist in pairs, locked in gravitational dances that can last millions or billions of years. If one member of such a pair emitted radio waves, the orbital motion might create periodic brightening and dimming as the geometry changed from our perspective. However, the math didn't quite work out. A 44-minute orbital period would place the two objects absurdly close together, almost certainly resulting in their merger rather than stable orbit, and the signal characteristics didn't match the predictions for such systems. The signal's location in the sky added another piece to the puzzle. It resided in the galactic plane, the flattened disk of our Milky Way where most stars congregate. This suggested a source within our own galaxy rather than something in the distant universe beyond, which helped constrain the possible distance and therefore the intrinsic brightness required to produce the observed signal strength. An object within our galaxy emitting this strongly in radio waves would need substantial energy reserves and efficient mechanisms for converting that energy into electromagnetic radiation. Dr. Hurley Walker and her colleagues published their findings in the journal Nature, presenting the data and their analysis while honestly acknowledging the profound uncertainty about the source's true nature. In science, it's perfectly acceptable to say, we don't know, when the evidence doesn't yet support a firm conclusion. The paper laid out what was observed, what explanations seemed most plausible, and what further observations would be needed to narrow down the possibilities. And so the astronomical community was presented with a challenge and an invitation. Here was a cosmic mystery, well documented and confirmed, waiting for someone to solve it, or at least to gather the pieces that would eventually lead to understanding. To fully appreciate the significance of a 44-minute signal, it helps to explore the landscape of periodic phenomena that astronomers have catalogued across the decades. The universe, despite its apparent chaos, contains numerous examples of regular rhythms, cosmic clocks driven by fundamental physics rather than conscious design. The most famous periodic sources are those pulsars we mentioned earlier, discovered somewhat accidentally by Jocelyn Bell Burnell and Anthony Hewish in 1967. Bell Burnell was a graduate student at the time, analysing radio telescope data on chart recorders, looking for the twinkling of radio sources caused by the solar wind. She noticed something unusual, perfectly regular pulses arriving from a fixed position in the sky, repeating every 1.3 seconds with such precision that the team briefly, half-jokingly labelled it LGM-1 for quote 1 before recognising it as a natural phenomenon. The discovery of pulsars transformed astrophysics, confirming theoretical predictions about neutron stars and providing natural laboratories for studying matter under conditions impossible to recreate on Earth. The fastest known pulsar spins 642 times per second, its equator moving at roughly 1/4 the speed of light, held together only by the immense gravitational pressure of its collapsed mass. The slowest confirmed radio pulsar has a period of about 12 seconds, already pushing the boundaries of what neutron star physics can easily explain. Then there are variable stars, objects whose brightness changes on regular cycles due to physical pulsations or eclipses. Cepheid variables, for instance, swell and contract over periods of days to weeks, their intrinsic brightness tied to the pulsation period in a relationship that makes them invaluable for measuring cosmic distances. These stars literally breathe, expanding and contracting as pressure and gravity compete, creating a rhythm as reliable as a heartbeat. Eclipsing binary stars provide another source of cosmic periodicity. Two stars orbiting so close that from our perspective they regularly pass in front of each other, creating dips in the combined brightness. The eclipse period directly reflects the orbital period, which can range from hours to years depending on the separation between the stars. Some binaries have been monitored for over a century, their orbital clocks ticking away with minimal variation. More recently, astronomers identified a class of objects called fast radio bursts, or FRBS, intense blasts of radio energy that last only milliseconds, but release as much energy in that brief flash as the sun produces in days. For years, FRBS were detected as one-time events, appearing once and never repeating, making them nearly impossible to study in detail. Then in 2016, astronomers confirmed the first repeating FRB, a source that sent multiple bursts from the same location in space, though without the precise regularity of our 44-minute signal. One particular repeating FRB, designated FRB 121102, became famous for its activity. Over years of observation, it produced hundreds of individual bursts, allowing detailed study of its properties. The bursts came in clusters, separated by periods of silence, but within those active periods the timing was irregular, sometimes multiple bursts in an hour, sometimes nothing for days. Scientists determined it originated from a dwarf galaxy 3 billion light-years away, associated with a persistent radio source and a region of intense magnetic fields. Theories emerged suggesting connections to young neutron stars, possibly magnetars, in complex environments. What made FRB 121102 particularly interesting was a discovery in 2020. The bursts exhibited a cyclical pattern with a period of about 160 days. The source would be active for 90 days, producing bursts irregularly during that window, then fall silent for 70 days before becoming active again. This longer timescale pattern suggested orbital motion, perhaps a neutron star in a binary system with a massive companion, though the exact mechanism remained and remains debated. Another enigmatic source, known as GCRTJ 1745-3009, was discovered in 2004. It emitted radio bursts lasting about 10 minutes, repeating every 77 minutes from a location near the galactic centre. Follow-up observations tried to catch it again but found nothing, as if it had turned off completely or was only intermittently active on timescales longer than individual observing sessions. The source remains unexplained, possibly related to our 44-minute mystery, possibly something entirely different. These examples illustrate that the universe contains periodic phenomena across a wide range of timescales, from milliseconds to months, each with its own underlying physics. The 44-minute signal sits in an unusual gap in this distribution. Too slow for conventional neutron star rotation, too fast for most orbital explanations, too regular for most variable phenomena. It occupies a sweet spot of mystery, and perhaps that's what makes it so compelling to contemplate as we drift towards sleep. As astronomers studied the 44-minute signal more carefully, they could definitively eliminate certain explanations, narrowing the field of possibilities even if they couldn't yet identify the correct answer. This process of elimination is crucial in science, as ruling out what something isn't often brings us closer to understanding what it is. First, researchers could confidently state this wasn't interference from Earth-based technology. Radio astronomy is perpetually plagued by human-generated signals, from satellites and aircraft to microwave ovens and electronic equipment. Modern civilization creates a constant background of radio noise that astronomers must filter out to detect faint cosmic sources. However, several factors argued against a terrestrial origin for this signal. The source position remained fixed on the sky over multiple observing sessions, moving only with the slow drift of stars through our galaxy's rotation, not with the rapid motion characteristic of satellites or aircraft. Earth-based interference would appear at different sky positions as the planet rotates, and as the source moves in Earth orbit or atmosphere. This signal stayed put, anchored to a specific celestial coordinate. Additionally, the signal's properties matched what we expect from cosmic radio sources rather than human technology. Its broad radio spectrum, its polarization characteristics, the way it scattered and dispersed as it passed through the interstellar medium between its source and Earth, all pointed to something truly astronomical rather than something generated in Earth's neighbourhood. Researchers also considered whether this might be some form of instrumental artifact, a ghost signal created by the telescope's electronics or data processing pipeline. Radio telescopes are complex instruments, and subtle bugs in software or quirks in hardware can occasionally create apparent signals that aren't actually there. The Discovery team carefully checked for these possibilities, analysing the raw data, examining the calibration procedures, confirming the detection with independent analysis methods. What convinced them the signal was real was its consistency across different observations and different data analysis approaches. When something is genuinely out there in space, it appears the same way regardless of exactly how you process the data within reasonable limits. An artifact, by contrast, often changes or disappears when you alter the analysis method, revealing its artificial nature. The 44-minute signal remained stubbornly present, unchanged in its fundamental properties, confirming it as a real astronomical source. The signal could also be ruled out as a known class of variable star or stellar phenomenon. Variable stars change their brightness due to internal pulsations, eclipses, or eruptions, but these occur in optical and infrared wavelengths primarily, with only weak radio emission if any. Our source was intensely radio bright but optically invisible, the opposite of what variable stars typically exhibit. Even exotic variables like cataclysmic binaries, where matter flows from one star onto another in violent accretion, don't produce the observed characteristics. Could it be a black hole? Black holes themselves don't emit radiation. Their gravity is so intense that nothing escapes, not even light, hence the name. But the material swirling around black holes, heating up as it spirals inward toward destruction, creates intense radiation across the electromagnetic spectrum. Active galactic nuclei, powered by supermassive black holes consuming entire stars, are among the brightest radio sources in the universe. However, these don't typically show the precise periodicity observed here, and the signal's location and properties didn't match the expected signatures of an active black hole system. Supernova remnants, the expanding shells of debris from exploded stars, also produce radio waves as they crash into surrounding interstellar material. But these are diffuse, extended sources rather than compact ones, and they don't pulse with regularity. A young pulsar within a supernova remnant might pulse regularly, bringing us back to the neutron star possibility. But as we discussed, the 44-minute period seems too long for standard pulsar physics. The process of elimination is both frustrating and exciting. Frustrating because each ruled-out possibility narrows the options without necessarily providing the answer. Exciting because it means we're potentially looking at something new, a phenomenon not yet catalogued, a piece of the cosmic puzzle we haven't encountered before. In astronomy, such discoveries occasionally overturn existing theories or reveal new physics operating at scales and energies we can't reproduce in laboratories. And this uncertainty, this acknowledgement that the universe still holds surprises for us, leads us naturally to contemplate what such discoveries mean for our understanding, and what questions they raise about what else might be out there, pulsing in the darkness, waiting for the right telescope to hear its call. Radio astronomy is, in many ways, an act of translation. The universe speaks in electromagnetic radiation, in wavelengths our bodies weren't designed to perceive, and we've built instruments to convert those invisible messages into forms we can analyse and understand. The Murchison Wide Field Array, the telescope that detected our mysterious signal, represents decades of technological refinement aimed at listening to the cosmos with ever-increasing sensitivity. Located in the Western Australian outback, the MWA occupies a site chosen for its remoteness from human radio interference. The array consists of 4,096 individual dipole antennas arranged in 256 tiles, each tile containing 16 antennas working together. These tiles are scattered across an area roughly 3 kilometres in diameter, a radio telescope as large as a small town, all listening in concert to capture faint whispers from space. Unlike optical telescopes with their mirrors and lenses, radio telescopes are often arrays of simple metal antennas, not dramatically different in principle from the antenna on an old television or radio, just vastly more sophisticated in how the signals are processed and combined. Each antenna converts incoming radio waves into electrical currents, tiny voltages that sophisticated electronics then amplify and digitize. Computers receive these digital signals from all the antennas simultaneously, combining them mathematically to create a coherent picture of the radio sky. This process, called interferometry, allows radio astronomers to achieve angular resolution far beyond what any single antenna could provide. By comparing the exact timing of when a radio wave arrives at different antennas, separated by known distances, the computer can determine the direction the wave came from with extraordinary precision. It's similar to how your brain uses the slight timing difference between sounds arriving at your two ears to locate the source of a noise, just implemented with hundreds or thousands of receivers instead of two. The MWA was specifically designed to study the early universe, particularly the epoch of ionization, when the first stars and galaxies formed and began transforming the cosmos from dark and neutral to transparent and ionized. To do this, it operates at relatively low radio frequencies, where the redshifted signals from that ancient era might be detected. These same low frequencies also make it sensitive to many other phenomena, from lightning on Jupiter to the radio emission from nearby stars and, as it turned out, mysterious periodic signals from unknown sources. When the MWA detected the 44-minute signal, it wasn't pointing at that particular patch of sky, because someone suspected something interesting there. The telescope was conducting a survey, systematically mapping large areas of sky to catalogue radio sources for various scientific purposes. The signal emerged from automated data analysis. Flagged by algorithms. Before we continue, most people will never know what you now know about the 44-minute signal. If that quiet feeling of understanding is something you want more of, this channel was built entirely for nights like this one. A like and subscribe takes 2 seconds and makes sure the universe keeps bringing you back here. Now let's go deeper into the signal. Flagged by algorithms designed to identify unusual or periodic sources among the thousands of radio objects detected in any given observation. This serendipitous discovery illustrates an important principle in modern astronomy. We don't always find what we're looking for. Sometimes we find what we weren't expecting, and those unexpected discoveries often prove most valuable. The cosmic microwave background radiation, the echo of the Big Bang itself, was discovered accidentally by 2 engineers trying to eliminate noise from a communications antenna. Pulsars were found during a survey looking for something completely different. The universe delights in surprising us when we're paying attention to what's actually there rather than what we expect to find. Following the initial detection, astronomers used other radio telescopes to confirm the signal and study it in more detail. The Murchison Wide Field Array continued monitoring it across multiple observing sessions, confirming that the 44-minute periodicity persisted over days and weeks. Other facilities, with different capabilities and sensitivities, added their observations, building a more complete picture of this mysterious source's properties. Each telescope brings unique capabilities to the investigation. Some observe at higher frequencies, testing whether the signal appears across the radio spectrum or only at specific wavelengths. Others have better angular resolution, potentially revealing whether the source is truly point-like or has some extended structure. Some can measure polarization more precisely, probing the magnetic fields at the source. The global network of radio telescopes becomes a collective instrument, far more powerful than any individual facility. Which brings us to consider the next piece of this puzzle. If we can detect and characterize this signal with our current technology, what might future instruments reveal? And what questions can we actually hope to answer? There's a profound honesty in astronomy about the limits of our knowledge, an acceptance that some questions cannot yet be answered with available technology and observations. For our 44-minute signal, these limitations shape what we can and cannot conclude, defining the boundaries of current understanding. Distance remains one of the fundamental uncertainties. Without knowing how far away the source is located, we cannot calculate its intrinsic brightness, its physical size, or its energy output, all crucial clues to its nature. Astronomers have several methods for determining cosmic distances, each with its own requirements and limitations. For relatively nearby objects within our galaxy, parallax provides the gold standard. Earth's orbit around the Sun gives us a baseline about 300 million kilometres wide. Astronomers measure a star's position very precisely at one time of year, then again 6 months later, when Earth is on the opposite side of its orbit. The apparent shift in position, viewed against more distant background stars, allows trigonometric calculation of the distance. However, this method only works for objects close enough to show measurable parallax, typically within a few thousand light years for the most precise measurements. For our radio source, if it's too faint in optical wavelengths to see with traditional telescopes, parallax measurements become impossible. We can't measure the shift in position of something we can't see. Some radio sources have been located precisely enough that radio interferometry could potentially measure parallax at radio wavelengths, but this requires extraordinarily precise observations and clear detection of the source over time, which hasn't yet been achieved for this particular object. Another distance indicator relies on the dispersion of radio waves as they pass through the interstellar medium. Space isn't truly empty. It contains about 1 atom per cubic centimetre on average, mostly hydrogen, along with free electrons and magnetic fields. Radio waves interact with these electrons, with higher frequencies travelling slightly faster than lower frequencies. By the time a radio pulse reaches Earth, different frequencies within that pulse have been delayed by different amounts, creating a measurable dispersion. The amount of dispersion depends on how many electrons the radio wave encountered along its path, which correlates roughly with distance. By measuring the dispersion and knowing the average electron density of interstellar space, astronomers can estimate how far the signal travelled. However, the interstellar medium isn't uniform. Electron density varies substantially from region to region, making distance estimates uncertain by factors of 2 or more in some cases. For the 44-minute signal, dispersion measurements provide a rough estimate but not a definitive distance. Without knowing the distance, we face ambiguity about the source's nature. Is it a relatively nearby object, perhaps a few hundred light years away, emitting modest amounts of radio energy? Or is it much farther, thousands of light years distant, requiring far more energy to appear as bright as it does? The two scenarios suggest very different types of objects with very different physics. We also don't know if the 44-minute period we observe represents the true repetition rate, or if it's been altered by the source's motion. Objects moving toward or away from us exhibit Doppler shifting, just like how a train's whistle changes pitch as it passes. For radio waves, motion toward us compresses the waves, increasing the frequency and potentially shortening any observed period. Motion away from us stretches the waves, decreasing frequency and potentially lengthening the period. If the source is in a binary orbit, for instance, the observed period might differ from the true period by a small but significant amount. Temperature, magnetic field strength, density, these physical properties of the source remain similarly uncertain. We can set some limits based on what we observe. The source must be compact enough to vary on timescales of seconds, which constrains its maximum physical size. It must have strong magnetic fields to produce the observed polarization. It likely involves relativistic particles, electrons moving near the speed of light, to generate radio waves efficiently. But precise values elude us. This uncertainty might feel frustrating, a failure to answer the fundamental question of what this thing is. But there's also something beautiful in the acknowledgement of limits, a recognition that the universe doesn't owe us easy answers, and that some mysteries persist not because we're not smart enough, but because we haven't yet gathered sufficient evidence. The scientific method isn't about declaring answers prematurely. It's about following the evidence wherever it leads and being honest when it hasn't yet led to a definitive conclusion. As we continue our exploration, we can find peace in this uncertainty, understanding that each astronomical mystery solved typically reveals several new questions, and the process of discovery is ongoing. Generations of astronomers building on the work of those who came before, gradually illuminating the darkness. Given the constraints and characteristics of the 44-minute signal, astronomers have proposed several theoretical explanations, each with supporting arguments and problematic aspects. These theories represent our best attempts to fit this unusual observation into the framework of known physics, stretching that framework where necessary to accommodate the unexpected. The most developed theory involves an unusual neutron star, possibly a magnetar, with properties at the extreme end of what current models allow. Standard neutron star physics suggests these objects can't maintain stable rotation at 44-minute periods, but perhaps under certain conditions this boundary could be pushed. If a magnetar had an extraordinarily strong magnetic field, even by magnetar standards, the magnetic pressure might interact with the star's rotation in complex ways we don't fully understand. Some researchers have proposed that the source might be in a state called to underscore, quote, underscore 2, underscore a theoretical object that hasn't been definitively observed before, but doesn't violate fundamental physics. The idea is that certain magnetars, under specific conditions of magnetic field configuration and rotational energy, could settle into slower rotation states while maintaining sufficient energy to produce periodic radio emission. The 44-minute period might represent a slow rotation rate, with radio beams sweeping across Earth once per rotation, or it might reflect some more complex emission pattern. Supporting this theory is the signal's polarization, which suggests strong magnetic fields, and its radio brightness, which requires efficient energy conversion mechanisms of the sort magnetars can provide. Challenging the theory is the rarity of such objects if they exist. We should perhaps have found more examples by now, and the lack of high-energy emission that magnetars typically produce alongside radio waves. Another possibility involves a binary system of white dwarfs, dense stellar remnants less extreme than neutron stars but still exotic by everyday standards. If two white dwarfs orbit closely enough, they might interact magnetically or through mass transfer in ways that could produce periodic radio emission. The orbital period would need to be 44 minutes, placing them extremely close together, almost touching, which is rare but not impossible. White dwarf binaries are known to exist at short periods, some completing orbits in minutes, spiraling ever closer as they radiate gravitational waves, those ripples in space-time itself that carry energy away from the system. Perhaps our signal comes from such a system at a particular stage of evolution, exhibiting behaviour we haven't observed before because we haven't studied enough examples. This theory has appeal but struggles to explain the specific characteristics of the radio emission, which don't quite match what models predict for white dwarf binaries. A more exotic proposal suggests we might be seeing a pulsar transitioning between different emission states. Some pulsars are known to mode switch, abruptly changing their pulse profile or brightness level, sometimes turning off completely for periods before reactivating. If a pulsar were switching on for brief periods, emitting radio waves, then switching off for 44 minutes before turning back on, it might produce something resembling the observed signal. However, known mode-switching pulsars don't show this level of regularity in their switching timescale, and the theory requires explaining why the off-time is so precisely 44 minutes. There's also speculation about whether this could represent a previously unknown class of astronomical object, something not yet in our catalogues of cosmic phenomena. The universe has surprised us before with objects like pulsars, quasars, magnetars, all of which were theoretical impossibilities until they were observed. Perhaps the 44-minute signal comes from a new type of stellar remnant, a different configuration of matter and energy that existing theories haven't predicted but that nature has somehow created. This possibility is simultaneously exciting and challenging. Exciting because discovering genuinely new classes of objects fundamentally advances our understanding of what's possible in the universe. Challenging because proposing a new type of object requires extraordinary evidence and careful theoretical work to demonstrate it doesn't violate well-established physical laws. Astronomers are appropriately cautious about claiming to have found something entirely new versus something that's a rare or extreme example of a known class. Each of these theories makes predictions that can potentially be tested with further observations. If it's a long-period magnetar, we might detect X-rays or gamma rays during detailed observations with space-based telescopes. If it's a white dwarf binary, optical telescopes might spot the faint glow of the stellar remnants if we know exactly where to look. If it's a mode-switching pulsar, we might catch it in different states with prolonged monitoring. The work continues, observation by observation, building the case for or against each possibility. Once astronomers identified one source pulsing every 44 minutes, the obvious question became, are there others? Is this a unique cosmic oddity, or does it represent a population of similar objects that have simply gone unnoticed until now? The search for related sources began almost immediately after the initial discovery was announced. Radio sky surveys provide the most promising hunting grounds. Over the past decades, astronomers have conducted increasingly comprehensive surveys of the radio sky, cataloguing millions of sources. Many of these sources received only brief observation, enough to detect them and record their position and brightness, but not enough to catch periodic behaviour if the period is long like 44 minutes. Detailed analysis of archival survey data might reveal other sources with similar characteristics that were present in the data all along, but never recognised as unusual. One of these newly identified sources, designated GLEAM-X J162759.5-523504.3, emits radio pulses approximately every 2 hours and 11 minutes. Like the 44-minute source, it's radio bright during its active phase, but completely invisible at other wavelengths. Its pulses show similar polarization characteristics and spectral properties, suggesting a related emission mechanism, even though the period is 3 times longer. Another source appears to pulse every 18 minutes, making it faster than the original, but still far slower than conventional pulsars. The discovery of this source was particularly satisfying for theorists, as it helps fill in the gap between normal pulsars and the ultra-long period sources, suggesting a continuum of objects rather than isolated mysteries. If there's a smooth distribution of periods, it implies a single underlying mechanism operating under various conditions rather than multiple unrelated phenomena. The emerging picture is that there might be dozens or hundreds of these long-period radio sources scattered throughout our galaxy, most still undetected because our surveys haven't had the sensitivity and patience to catch them. Each object pulses in its own rhythm, some fast, some slow, all ticking away in the darkness, largely invisible until radio telescopes happened to be watching when they brightened. This raises intriguing questions about why we're finding these objects now. Have they always been there, and we simply lack the instruments to detect them? Or is there something happening in our current cosmic epoch that makes these sources more common or more active than they were in the past? The former seems more likely, given that radio astronomy is a relatively young field, barely 70 years old, and our survey capabilities have improved dramatically in just the last decade. The Square Kilometre Array, currently under construction in Australia and South Africa, will eventually provide unprecedented sensitivity and survey speed for radio astronomy. When completed, it will detect sources far fainter than current telescopes can see, and will conduct all sky surveys with a completeness that today's instruments cannot match. Astronomers expect the SKA to revolutionize our understanding of these long-period sources, potentially detecting thousands of examples and allowing detailed statistical studies of their properties. But we need not wait for future facilities. Current telescopes, including the MWA, continue monitoring these sources, building up long-term light curves that show how their behaviour evolves over months and years. Does the 44-minute period stay exactly constant, or does it slowly change, perhaps speeding up or slowing down? Do the sources always pulse, Or are there times when they go dormant? These questions can be answered with patience and systematic observation. There's also interest in coordinating observations across multiple telescopes operating at different wavelengths. If a source pulses in radio waves every 44 minutes, what about X-rays or optical light? Simultaneous observations across the electromagnetic spectrum could reveal correlations that point toward the underlying mechanism. Space-based X-ray observatories like NASA's Chandra or ESA's XMM Newton could be pointed at these sources during their radio-bright phases, searching for corresponding X-ray emission that might confirm or rule out magnetar-like properties. And as we gather more data, more examples, more detailed observations, we move incrementally closer to understanding, each new piece of information constraining the possibilities, narrowing the field of viable theories. The story of the 44-minute signal, independent of its ultimate explanation, teaches valuable lessons about science, discovery, and our relationship with the unknown. These lessons extend beyond astronomy, offering insights into how we approach mysteries and uncertainty in all aspects of inquiry. First, it reminds us that comprehensive surveys matter. The signal was discovered not through targeted observation of a suspected interesting object, but through systematic mapping of the sky. So many astronomical discoveries happen this way, unexpected finds in routine survey data that reveal phenomena no one predicted. This argues for continued investment in survey science, in methodically cataloguing the contents of the universe, rather than only studying objects we already know about. Modern astronomy increasingly relies on data mining and machine learning algorithms to identify unusual patterns in vast datasets. The sheer volume of data from contemporary telescopes exceeds human capacity to examine directly. With surveys generating terabytes of information every night, automated analysis systems process this flood of data, flagging anomalies and periodic sources for human attention. The 44-minute signal emerged from such automated analysis, showcasing the power of computational approaches to discovery. However, the story also demonstrates the irreplaceable role of human judgment and expertise. Automated systems flagged the signal as unusual, but experienced astronomers were needed to interpret what that meant, to design follow-up observations, to connect the observations with theoretical models, to recognize the profound implications of what might otherwise seem like just another entry in a catalogue of radio sources. The collaboration between computational power and human insight drives modern astronomical discovery. The signal's mystery also highlights how much we still don't know about the universe, despite centuries of astronomical observation and decades of sophisticated space-based measurements. We've mapped the cosmic microwave background with exquisite precision, detected gravitational waves from colliding black holes a billion light-years away, imaged the shadow of the supermassive black hole in M87. Yet a radio source in our own galaxy, probably within a few thousand light-years of Earth, can still puzzle us. This humility about the limits of knowledge seems appropriate and healthy. The universe is vast and complex, operating across scales from subatomic particles to cosmic horizons, governed by physical laws we understand well in many regimes but incompletely in extreme conditions. Neutron star interiors, for instance, contain matter compressed to densities where quantum mechanics and nuclear physics become entangled in ways we can't fully model. Laboratory physics can't reproduce these conditions, so we rely on astronomical observations of neutron stars to test our theories. The discovery process also illustrates the value of international collaboration and open sharing of data. The Murchison Wide Field Array is a collaboration involving multiple universities and research institutions across several countries. When the signal was detected, the data were shared with the broader astronomical community, inviting worldwide participation in follow-up observations and theoretical interpretation. Science advances most rapidly when knowledge flows freely and researchers build on each other's work. There's also something profound about the patience required for this kind of science. The signal has been pulsing for an unknown length of time, possibly centuries or millennia, before we happen to notice it. It will likely continue pulsing long after current observational campaigns end. Astronomy often involves timescales that dwarf human lifespans, studies that span generations of researchers, questions that may not be fully answered within any individual career. This long-term perspective, this acceptance of working on problems knowing you might not see the final answer, represents a particular kind of dedication. Finally, the signal reminds us that wonder and mystery are not incompatible with scientific understanding. Some worry that explaining natural phenomena removes their magic, that knowing how something works diminishes its beauty. But the 44-minute signal demonstrates the opposite. The more we learn about it, the more intriguing it becomes. Each new detail raising new questions, each constraint on its properties making the remaining possibilities more remarkable. Scientific knowledge doesn't eliminate mystery, it often deepens it, revealing layers of complexity and wonder invisible to casual observation. As we continue our journey through this topic, moving from the specifics of the signal itself to broader questions about cosmic communication and the search for understanding, we can carry these lessons forward, appreciating both what we know and what remains beautifully uncertain. The 44-minute signal exists within a much larger context of radio waves filling the universe, natural broadcasts from countless sources spanning cosmic history. To truly appreciate this particular mystery, it helps to understand the rich radio environment Earth inhabits, the electromagnetic symphony playing constantly in frequencies our bodies cannot perceive but our instruments detect. The cosmic microwave background provides the quietest, most pervasive radio signal, filling all of space with the cooled radiation from the Big Bang itself. This faint glow, now shifted into microwave frequencies after 13.8 billion years of cosmic expansion, appears the same in every direction, with only tiny fluctuations, the seeds of all structure that later formed. It's the closest thing to silence in the radio universe, a baseline against which all other sources stand out. Our own sun broadcasts continuously in radio wavelengths, its outer atmosphere seething with magnetic activity that generates radio waves. Solar flares and coronal mass ejections create sudden bursts of radio energy that sweep past Earth, sometimes interfering with radio communications and GPS signals. Studying solar radio emission helps us understand stellar magnetic fields and predict space weather that can affect satellites and power grids. Jupiter rivals the Sun in radio brightness despite being much smaller and receiving much less energy. The giant planet's powerful magnetic field, fed by electrical currents in its metallic hydrogen interior, creates intense radiation belts that emit radio waves. Jupiter's moon, Io, adds to the show, its volcanoes spewing charged particles into Jupiter's magnetosphere, creating auroral displays far more powerful than Earth's northern lights, accompanied by intense radio emissions that amateur radio astronomers can detect with modest equipment. Pulsars, those rapidly spinning neutron stars we discussed earlier, collectively create a vast population of cosmic radio sources. Over 2,000 pulsars have been catalogued in our galaxy, each with its own rotation rate and pulse profile. Some are isolated, remnants of ancient supernova explosions now spinning alone through space. Others orbit companion stars in binary systems, their gravitational interaction creating complex dynamics that affect their spin rates over time. The centre of our Milky Way galaxy hosts Sagittarius A star, a supermassive black hole with a mass of 4 million suns, while black holes themselves don't emit radiation. The superheated material swirling around Sagittarius A star creates radio waves that radio telescopes can detect. The Event Horizon Telescope famously imaged this black hole shadow in 2022, combining radio observations from telescopes across the entire Earth to achieve the angular resolution needed to see the structure at the event horizon's edge. Beyond our galaxy, radio waves arrive from cosmic distances, Many sources so far away their light has travelled for billions of years to reach us. Active galactic nuclei, powered by supermassive black holes consuming material at prodigious rates, can outshine entire galaxies in radio wavelengths. Some launch jets of particles and magnetic fields that extend for millions of light years, creating double-lobed radio structures visible across vast cosmic distances. Radio galaxies like Centaurus A show these lobes beautifully in radio images, the central active nucleus feeding twin jets that inflate enormous bubbles of radio-emitting plasma far into intergalactic space. These structures persist for millions of years, slowly fading as they expand and cool, monuments to the power that black holes can wield when fed sufficient material. Quasars, the most luminous persistent sources in the universe, shine brilliantly in radio wavelengths alongside their intense optical and X-ray emission. These objects represent supermassive black holes in the early universe, seen as they were billions of years ago when galaxies were younger and black hole feeding was more common. Their radio emission carries information about the distant past, about conditions in the cosmos when the universe was a fraction of its current age. Gamma-ray bursts, the most energetic explosions since the Big Bang, produce brief but intense radio afterglows that fade over days to weeks. These cataclysmic events caused by the collapse of massive stars or the collision of neutron stars create shock waves that plough through surrounding material, accelerating particles and generating radio waves. Studying these afterglows helps astronomers understand the extreme physics of these explosions and the environments where they occur. Even seemingly empty intergalactic space contains faint radio emission, synchrotron radiation from cosmic ray particles spiraling around magnetic fields that thread the space between galaxies. This diffuse radio background provides clues about the large-scale structure of the universe and the magnetic fields that pervade cosmic voids. Within this rich radio environment, the 44-minute signal represents one more voice, distinctive in its regularity and mysterious in its nature. It's both part of the cosmic radio chorus and uniquely itself, a puzzle piece that doesn't quite fit existing categories, yet clearly belongs to the natural universe, rather than being something artificial or anomalous in the fundamental physics sense. Whenever astronomers detect unusual signals from space, particularly those with regular patterns, a certain question arises inevitably, even though most scientists consider it highly unlikely. Could this be a signal from extraterrestrial intelligence? It's a question worth addressing directly and thoughtfully, rather than dismissing out of hand or treating with excessive speculation. The search for extraterrestrial intelligence, SETI, has a long and scientifically respectable history, despite sometimes being treated as fringe science. The possibility that we're not alone in the universe, that other technological civilizations might exist among the hundreds of billions of stars in our galaxy, seems less like wild speculation and more like statistical probability when you consider the numbers involved. If life emerged on Earth, if intelligence and technology developed here, similar processes might occur elsewhere given appropriate conditions. SETI researchers have spent decades listening to the cosmos, searching for signals that show characteristics of artificial origin rather than natural astrophysical processes. The challenge is distinguishing potential technosignatures from the countless natural radio sources that fill the sky. A truly artificial signal would presumably show certain features that natural sources rarely or never exhibit: narrow bandwidth, drift rates consistent with transmission from a rotating planet, modulation patterns that encode information, perhaps mathematical relationships in frequencies chosen. The 44-minute signal lacks these characteristics. Its broad radio spectrum, its polarization properties, its overall behaviour all match what we expect from natural astrophysical sources, even if we haven't pinpointed which specific type. There's no modulation suggestive of information encoding, no mathematical precision in the frequency structure, no drift pattern consistent with an exoplanetary transmission. By the criteria SETI scientists use, this signal appears natural rather than artificial. Moreover, the signal's periodicity alone doesn't suggest intelligence. The universe contains numerous examples of natural clocks, as we've discussed, from pulsar rotation to orbital periods, all maintaining regular rhythms without conscious design. Evolution favoured human pattern recognition. We see faces in clouds and meaning in coincidences, a tendency that served our ancestors well when noticing patterns meant survival, but can mislead us into seeing design where only physics operates. Still, the question _3_ reflects something deeper than naive hope for extraterrestrial contact. It acknowledges our cosmic loneliness, our uncertainty about whether intelligence is common or rare in the universe, our desire to know if Earth's story of life and consciousness has been repeated elsewhere. These are profound questions, worthy of serious scientific investigation rather than dismissive mockery. The most famous potential alien signal, the WOW signal detected in 1977, remains unexplained despite decades of follow-up searches. Astronomer Jerry Eman detected it using Ohio State University's Big Ear radio telescope, a strong narrow-band radio signal at 1420 MHz, the frequency of neutral hydrogen's emission line. The signal lasted 72 seconds, the maximum time the telescope's beam could observe any fixed point in the sky as Earth's rotation carried it past. Eman famously wrote "wow" in the margin of the computer printout giving the signal its name. Attempts to detect the WOW signal again have all failed. The same patch of sky has been observed hundreds of times at the same frequency, with more sensitive equipment, but the signal never repeated. This non-repetition argues against an artificial origin. We'd expect an intentional beacon to repeat, but it doesn't definitively rule out something extraordinary. Perhaps it was a one-time transmission, or perhaps Earth moves through a narrow beam only rarely. The 44-minute signal differs fundamentally from WOW in that it repeats reliably and has been confirmed through multiple observations. If it were artificial, that would imply an enormous transmitter, operating continuously for years at least, broadcasting with substantial power in radio wavelengths. While not physically impossible, it seems unlikely that an extraterrestrial civilization would devote such resources to transmitting with no clear information content, no obvious attempt to attract attention through meaningful patterns. Scientists involved in SETI research have examined the 44-minute signal and concluded it almost certainly represents a natural astrophysical phenomenon, interesting for what it tells us about the universe, but not evidence of extraterrestrial intelligence. This conclusion doesn't stem from unwillingness to consider the possibility, but from careful analysis of the signal's characteristics against established criteria for distinguishing natural from artificial sources. The search for extraterrestrial intelligence continues through multiple programs using various approaches. The SETI Institute operates targeted searches, pointing radio telescopes at nearby sun-like stars that might host habitable planets. Breakthrough, Listen, funded by Yuri Milner, conducts the most comprehensive search to date, surveying millions of stars across multiple radio frequency bands. These programs have so far detected no confirmed artificial signals, but the search has barely begun when you consider how many stars exist and how many frequencies might be used for communication. Perhaps the most important aspect of the SETI question is what it reveals about human curiosity and our need for connection. We look to the stars partly to understand physics and chemistry and cosmic history, but also to know whether we're alone. The question carries emotional weight alongside its scientific merit, touching on our place in the cosmos and the possibility of profound connection across the void. For the 44-minute signal, the answer appears clear: natural astrophysical source, not extraterrestrial communication. But the asking of the question, the consideration of possibilities, the process remains valuable and distinctly human. The history of astronomy is rich with accidental discoveries, observations that weren't part of any planned search, but that fundamentally changed our understanding of the universe. The 44-minute signal joins this tradition, and examining other serendipitous discoveries provides context for appreciating how science sometimes advances through fortunate chance as much as deliberate investigation. Perhaps the most famous accidental discovery in astronomy is the cosmic microwave background radiation itself. In 1964, Arno Penzias and Robert Wilson, engineers at Bell Telephone Laboratories, were trying to eliminate excess noise from a radio antenna designed for satellite communications. No matter what they did, they couldn't get rid of a persistent faint hiss coming equally from all directions in the sky. They checked everything. They cleaned out pigeon droppings from the antenna. They pointed it at different parts of the sky. They measured at different times of day and different seasons. The signal remained, quiet but unmistakable, about 3 degrees Kelvin above absolute zero, uniform across the entire observable sky. Eventually, they learned of theoretical predictions by Robert Dicke and colleagues that the Big Bang should have left exactly such a signal. Penzias and Wilson had accidentally detected the echo of creation itself, earning them the Nobel Prize in Physics in 1978. Pulsars, those rapidly spinning neutron stars, were also accidental discoveries. Jocelyn Bell Burnell, then a graduate student at Cambridge University, was studying interplanetary scintillation, the twinkling of radio sources caused by the solar wind. In August 1967, she noticed unusual scruff on the chart recorder paper, a regular signal that appeared around the same time each night. Detailed analysis revealed pulses arriving every 1.337 seconds with incredible precision. The regularity was so striking that the team briefly considered whether it might be an artificial signal from an extraterrestrial civilization, labelling it LGM-1 for quote 6 before rejecting that hypothesis. Bell Burnell discovered 3 more pulsating sources in different parts of the sky, making an alien explanation unlikely, unless the galaxy was filled with broadcasting civilizations, all using the same technology. The pulsars turned out to be rapidly rotating neutron stars, objects whose existence had been theoretically predicted but never observed. Gamma-ray bursts were discovered accidentally by military satellites designed to detect nuclear weapons tests. The Vela satellites, launched in the 1960s to monitor compliance with nuclear test ban treaties, carried gamma-ray detectors to spot the distinctive signature of nuclear explosions in space. In 1967, the satellites detected brief bursts of gamma rays that clearly weren't coming from Earth or anywhere in the solar system. The military kept the discovery classified for several years before publishing the findings in 1973. Scientists were baffled. The bursts came from random directions, lasted seconds to minutes, and released enormous energy in gamma rays. Decades of research eventually revealed that gamma-ray bursts represent some of the most energetic events in the universe. The birth cries of stellar-mass black holes and the collisions of neutron stars visible across billions of light-years. Uranus was discovered accidentally by William Herschel in 1781. Herschel was conducting a systematic survey of the sky with his homemade telescopes when he noticed an object that appeared as a disk rather than a point like stars do. He initially thought he'd discovered a comet, but careful observation of its motion revealed an orbit beyond Saturn's, making it the first planet discovered since ancient times. The discovery doubled the known size of the solar system at once. The first extrasolar planet orbiting a sun-like star was discovered through an accidental technique. Astronomers had been searching for exoplanets for decades without success when, in 1995, Michel Mayor and Didier Queloz detected a Jupiter-mass planet orbiting the star 51 Pegasi. They found it using precise radial velocity measurements, detecting the tiny wobble that a planet's gravity induces in its parent star's motion. What made the discovery surprising wasn't just finding an exoplanet, but its properties. The planet, now called 51 Pegasi b or Dimidium, orbits extremely close to its star, completing each orbit in just 4.2 days. This _7_ configuration contradicted all theoretical models of planetary formation at the time. No one expected to find giant planets so close to their stars. The discovery opened our eyes to the incredible diversity of planetary systems and launched the field of exoplanet science that has now catalogued thousands of worlds. Dark energy might represent the most profound accidental discovery in cosmology. In 1998, two teams studying distant supernovae to measure the universe's expansion rate made a shocking finding. Instead of slowing down as everyone expected due to gravitational attraction, the expansion was accelerating. Something, now called dark energy, was pushing the universe to expand faster and faster. This discovery overturned comfortable assumptions about the cosmos's ultimate fate. Instead of eventually collapsing in a big crunch or coasting to a halt, the universe will expand forever, galaxies racing away from each other at increasing speeds until, in the distant future, most galaxies will be beyond our observational horizon. Their light stretched and dimmed beyond detection. What unites these discoveries is the combination of careful, systematic observation with openness to the unexpected. The researchers were all engaged in legitimate scientific work, building instruments, conducting surveys, following up on theoretical predictions. But when their data showed something strange, something that didn't fit expectations, they had the wisdom and courage to investigate further rather than dismissing it as error or noise. As researchers have studied the 44-minute signal more carefully, they've been able to rule out additional possibilities with increasing confidence. This process of elimination continues to narrow the field of viable explanations, even as the true answer remains elusive. Understanding what the signal cannot be helps us appreciate the genuine mystery of what it is. The signal cannot be a distant quasar or active galactic nucleus. These objects, while incredibly luminous in radio wavelengths, don't show the precise periodicity observed here. When quasars and AGN vary in brightness, they do so irregularly, driven by chaotic accretion processes as material falls toward their central black holes. The variability timescales range from hours to years, sometimes showing quasi-periodic oscillations, but never the clockwork precision of the 44-minute source. Moreover, if the signal came from a distant galaxy billions of light-years away, the dispersion measure, that delay between different radio frequencies caused by free electrons along the path, would be enormous, far larger than observed. The relatively low dispersion measure indicates a source within our own galaxy, or perhaps in nearby satellite galaxies like the Magellanic Clouds, placing firm limits on its distance and cosmic context. The signal cannot be a conventional pulsar that we're viewing at an unusual angle or in an exotic emission mode. Decades of pulsar observations have established clear relationships between period, pulse width, spectral index, and other characteristics. The 44-minute source violates these relationships in ways that can't be explained by orientation effects or special viewing geometries. While it might represent some kind of neutron star, it would have to be a fundamentally different type than the pulsars we've catalogued over the past 50-plus years. It's also not a normal binary star system, where we're seeing orbital modulation of brightness. Binary systems can create periodic signals, but the periods relate to orbital mechanics in predictable ways. A 44-minute orbital period would require the two stars to be almost touching, orbiting their common centre of mass at tremendous speeds. Such close binaries do exist, systems called cataclysmic variables and X-ray binaries, where material transfers from one star to another, but these systems have characteristic signatures in multiple wavelengths that don't match our signal. This source isn't a flare star or other type of magnetically active star. Certain cool dwarf stars, particularly M dwarfs, can produce powerful magnetic flares that emit radio waves. These flares can be dramatic, releasing as much energy in minutes as the sun produces in days, but they're sporadic rather than periodic. They might repeat, but not with 44-minute precision maintained over weeks and months of observation. The regularity argues against stochastic magnetic activity and towards something with an inherent clock. Researchers have also considered whether the signal might result from some kind of eclipsing or occulting system, where another object regularly blocks the radio emission from a background source. This could potentially create periodic disappearances of a continuous radio source, but the observations show the opposite pattern. The source appears periodically against a silent background, rather than disappearing periodically from continuous visibility. The emission itself is periodic, not its visibility. The possibility of gravitational lensing causing periodic brightening has been examined and rejected. Gravitational lensing occurs when a massive object's gravity bends light from a more distant source, sometimes creating multiple images or enhancing brightness. In rare cases, lensing can create periodic variations if the lens, source, and observer move in particular ways. However, this requires specific geometric configurations and relative motions that don't match the observed characteristics of the 44-minute signal. It's not a spacecraft or satellite, either human-made or hypothetically alien. Human spacecraft and satellites move across the sky relatively rapidly, their positions changing noticeably over hours or days from Earth's perspective. The 44-minute source maintains a fixed position among the stars, moving only with the slow galactic rotation that shifts stellar positions by tiny amounts over years. Any spacecraft or satellite creating this signal would need to be maintaining a precise position in space relative to the distant stars, an enormous ongoing expenditure of fuel that seems implausible for either human technology or any reasonable alien engineering. The signal also doesn't match the expected characteristics of exotic objects like primordial black holes, cosmic strings, or other speculative phenomena from the edges of theoretical physics. While we can't absolutely rule out involvement of unknown physics, the burden of proof for such extraordinary claims is appropriately high. The signal's properties can be explained with known physics even if we haven't identified the exact mechanism, making appeals to exotic new physics premature. What remains after all these eliminations is a short list of possibilities, all involving stellar remnants of one kind or another, likely neutron stars in unusual configurations or states. The precision of the timing argues for something with intrinsic rotational or orbital periodicity rather than random processes. The radio brightness requires efficient energy conversion mechanisms of the sort we know operate in neutron star magnetospheres. The source must be relatively nearby in cosmic terms within our galaxy, making it accessible to detailed study if we can gather sufficient observations. This narrowing of possibilities represents progress even without a definitive answer. Each ruled-out explanation removes uncertainty, constraining the parameter space within which the truth must lie. Behind the observations and theories lies a framework of mathematics that allows astronomers to quantify the signal's properties and test hypotheses with precision. Understanding the mathematical tools astronomers use to analyse signals like this reveals the rigorous methodology behind the seemingly simple statement _8 periodicity detection begins with time series analysis, examining how a signal's brightness changes over time. Astronomers use techniques like Fourier analysis, which decomposes any complex periodic signal into a sum of simple sine waves at different frequencies. If a true periodicity exists in the data, it will show up as a peak in the Fourier power spectrum at the corresponding frequency. For the 44-minute signal, the Fourier transform shows a strong peak at a frequency of 0.0003787 Hz, corresponding to one cycle every 2,640 seconds. The stability of the period over time provides another crucial constraint. If observations separated by weeks or months continue to phase up correctly, meaning the pulses arrive when predicted based on earlier timing, the period must be stable to within the measurement uncertainty. For the 44-minute signal, the period appears stable to within a few seconds over months of observations, though more data are needed to detect slow period evolution that might reveal whether the source is spinning up or down. Dispersion measure analysis requires solving the relationship between arrival time delay and radio frequency. Higher frequencies arrive slightly earlier than lower frequencies due to interaction with free electrons in the interstellar medium. By measuring how arrival time varies with frequency, astronomers can calculate the integrated electron column density along the line of sight, which provides a rough distance estimate when combined with models of the galaxy's electron distribution. The mathematics becomes particularly interesting when considering possible emission mechanisms. Models of neutron star magnetospheres involve solving Maxwell's equations for electromagnetic fields in the presence of strong gravity and rapid rotation. These are complex partial differential equations that generally require numerical solutions on supercomputers. The results predict beam patterns, polarization, and spectral properties that can be compared with observations. For binary systems, orbital mechanics provides testable predictions. Kepler's laws relate orbital period to the masses and separation of the components. For a 44-minute orbital period, the mathematics tells us the two objects must be separated by roughly the diameter of Earth, incredibly close for stellar objects. The orbital velocity would be thousands of kilometers per second, approaching a significant fraction of the speed of light for white dwarf or neutron star masses. Statistical analysis helps evaluate competing theories. Bayesian inference provides a framework for calculating the relative probabilities of different models given the observed data. Each model makes specific predictions for various observable quantities: period, brightness, spectral index, polarization, and so on. The model whose predictions best match the actual observations receives the highest probability, though all models might have low absolute probabilities if none is particularly good. The mathematical framework also reveals what additional observations would be most valuable. Information theory quantifies how much uncertainty different measurements could resolve. For instance, precise distance measurements would dramatically constrain possible models by pinning down the absolute luminosity. Continuous monitoring might catch period changes that reveal whether rotational or orbital energy is being lost. Multi-wavelength observations would test predictions about associated X-ray or optical emission. As we move deeper into our exploration, the mathematics remains in the background, a rigorous foundation supporting the more qualitative descriptions. Ensuring that when scientists say they're confident about certain conclusions, the confidence rests on solid quantitative analysis rather than just intuition or hope. There's something deeply reassuring about discovering regularity in the universe, a cosmic clock ticking steadily in the darkness, indifferent to human concerns yet somehow comforting in its reliability. The 44-minute signal, whatever it ultimately proves to be, represents one more example of the universe's tendency toward patterns and order emerging from apparently chaotic conditions. This pattern finding goes deep in human nature. Our ancestors survived partly by recognizing patterns in the natural world. The progression of seasons, the phases of the moon, the movement of stars across the night sky marking the passage of time and the arrival of planting or harvesting seasons. We're pattern recognition machines. Our brains evolved to detect regularities and use them to predict future events and plan accordingly. The rhythms of the cosmos offer patterns at every scale. Earth rotates once per day, creating the cycle of day and night that governs biological rhythms for nearly all surface life. The moon orbits Earth monthly, its phases marking time, driving tides through gravitational interaction. Earth orbits the sun yearly, creating seasons through the tilt of its rotation axis relative to the orbital plane. These patterns feel stable and eternal from human perspectives, though we know they change very slowly over long time scales. Earth's rotation gradually slows due to tidal friction with the moon, lengthening the day by about 1.7 milliseconds per century, imperceptible in a human lifetime but significant over geologic epochs. The moon slowly recedes from Earth, about 3.8 centimeters per year, gradually weakening tides and lengthening the month far into the future. The planets follow predictable orbits around the Sun, their positions calculable centuries into the past or future using Newton's laws of motion and gravity, later refined by Einstein's general relativity for precise predictions. Ancient astronomers could predict eclipses and planetary configurations because celestial mechanics is fundamentally regular and deterministic within our solar system, chaos theory notwithstanding for very long timescales. Stars themselves are clocks of a kind. They burn their nuclear fuel at rates determined by their masses and compositions, evolving through predictable stages from birth in nebulae to death as white dwarfs, neutron stars or black holes. A star like the Sun will live roughly 10 billion years on the main sequence, fusing hydrogen to helium in its core. More massive stars burn brighter and die younger, while less massive stars conserve their fuel and might shine for trillions of years, longer than the current age of the universe. There's aesthetic pleasure in this discovery. 90 minutes in, still here. You chose this over everything else the internet was offering you tonight, and that says everything. There are not many of us who end our days this way, learning something real, drifting somewhere peaceful. A like and subscribe helps this channel find more people like you, people who deserve a quiet place to land at the end of the day. Now, back to the stars. There's aesthetic pleasure in this discovery, beauty and precision, satisfaction in detecting order within apparent chaos. The universe might be filled with random events and statistical processes, but it also contains islands of determinism, regularities that persist across vast timescales, patterns we can measure and predict and contemplate. In a cosmos that can seem overwhelmingly large and indifferent, these patterns offer handholds for understanding, ways to feel connected to the machinery of creation. As we rest here in this thought, considering the comfort of cosmic clockwork and the pleasure of discovering regularity, we can appreciate both the intellectual satisfaction of pattern recognition and the deeper emotional resonance of feeling that the universe, while vast beyond imagining, operates according to comprehensible principles that human minds can grasp and describe. Astronomy cultivates a particular kind of patience, a willingness to work on problems whose solutions might not emerge for years or decades, to contribute pieces to puzzles knowing you might not see the completed picture. The 44-minute signal exemplifies this aspect of astronomical research, a mystery that will likely require extended observation campaigns and theoretical development before yielding to complete understanding. Consider the timescales involved in confirming the signal's properties. To establish that the 44-minute period is genuinely stable requires observations spanning months or years, checking whether each pulse arrives when predicted based on earlier timing. If the period changes, whether speeding up or slowing down, detecting the evolution requires patient accumulation of data points, each observation adding to the statistical significance of any trend. The period might be changing very slowly, perhaps losing 1 second per year as rotational energy radiates away, or gaining time if some mechanism transfers energy into the rotation. Detecting such subtle changes requires both precise measurements and long baselines. One observation tells you almost nothing about period evolution. 10 observations over a month set initial constraints. 100 observations over a year might detect relatively fast changes. Really establishing long-term behaviour requires dedication spanning the careers of individual astronomers. This patience extends beyond timing measurements. Understanding the signal's nature might require technological developments not yet realised. Instruments with capabilities beyond current facilities. The original radio sources detected in the 1930s and 40s couldn't be studied in detail until much more sensitive radio telescopes were built in the 50s and 60s. Cosmic microwave background measurements became precise only with satellite observatories like COBE, WMAP and Planck, each generation improving sensitivity by orders of magnitude. The search for gravitational waves required even more patience. Einstein predicted their existence in 1916, but detecting them required technology inconceivable at that time. early experiments in the 1960s and 70s proved too insensitive. Joseph Weber's claimed detections in the 1970s couldn't be confirmed and are now considered instrumental artifacts. It took until September 2015, nearly a century after prediction, for LIGO to finally detect gravitational waves from merging black holes, confirming Einstein's century-old theoretical work. Thousands of scientists contributed to that century-long quest, most working on problems that had no guarantee of solution in their lifetimes. They built instruments, developed theory, trained students, wrote proposals for funding. Knowing that the final detection might come after they retired or died, yet they persisted, driven by conviction that the question mattered and that science progresses through accumulated small steps, even when giant leaps seem distant. The astronomers studying the 44-minute signal join this tradition. They publish what they know, making the data available to others. They continue observing when telescope time permits, adding data points to the growing curve. They develop theoretical models and discuss the implications at conferences and in journal articles. They train graduate students who might carry the investigation forward using tools not yet built. This patience isn't resignation or passivity. It's active dedication to long-term goals, recognition that some questions can't be answered quickly regardless of effort, and commitment to advancing knowledge incrementally. It's trusting that someone will eventually solve the puzzle even if that someone isn't you, and being content with contributing whatever pieces you can. There's something profoundly human about this patience, this willingness to work toward goals beyond individual lifetimes, to plant trees whose shade you'll never enjoy. It connects astronomical research to other grand human projects, building cathedrals that took generations to complete, writing encyclopedias that required decades of scholarship, preserving knowledge through dark ages for future enlightenment. Stepping back from the technical details of the 44-minute signal, we can contemplate what its existence means from broader cosmic perspectives, how it fits into the larger story of the universe, and our attempts to understand our place within it. The signal originates from somewhere in our galaxy, the Milky Way, a barred spiral galaxy containing roughly 200 to 400 billion stars, along with vast quantities of gas, dust, dark matter, and myriad planets orbiting those stars. Our solar system resides in a minor spiral arm about 2/3 of the way from the galactic centre to the edge, orbiting the centre at roughly 200 kilometers per second, taking about 230 million years to complete one orbit. From this perspective, the 44-minute source is a neighbour in cosmic terms. If it's a few hundred light years away, it's practically in our stellar backyard, closer than most stars visible to the naked eye. If it's a few thousand light years distant, it's still within our local galactic neighbourhood, part of the same broader structure we inhabit. The radio waves we detect began their journey when the source was in almost exactly the same location relative to us that it occupies now, since even thousands of light years of travel time represents only a tiny fraction of galactic orbital periods. This proximity makes the signal more accessible to study than most cosmic phenomena. We can potentially observe it in detail with existing or near-future instruments. If we eventually identify its nature, we might find many more examples scattered throughout the galaxy, building up statistical samples that reveal how common such objects are, what conditions create them, how they evolve over time. The signal also connects to the broader question of stellar evolution and endpoints. Stars are born in collapsing clouds of gas and dust, live their lives fusing lighter elements into heavier ones in their cores, and eventually die in ways determined by their initial masses. Low-mass stars like red dwarfs burn hydrogen slowly and might shine for trillions of years. Sun-like stars expand into red giants before shedding their outer layers and leaving white dwarf cores to slowly cool over billions of years. Massive stars explode as supernovae, creating neutron stars or black holes from their collapsed cores. Our mysterious source almost certainly involves one of these stellar endpoints, most likely a neutron star of some variety. If confirmed, it adds to our census of these exotic objects and potentially reveals a new mode of behaviour or evolutionary state we hadn't previously documented. Each new class of object discovered tells us something about the range of possible outcomes from stellar evolution, about the variety of ways stars can end their lives and what remnants they leave behind. There's also a temporal perspective to consider. The signal presumably has a history, a beginning, and perhaps eventually an end. It wasn't always pulsing every 44 minutes. At some point in the past, this behaviour started perhaps when a supernova created the neutron star, or perhaps much later as the neutron star's rotation slowed to a critical threshold, or perhaps when some other initiating event occurred. How long will it continue? If it's powered by rotational energy, the source will gradually spin down, slowing as it radiates energy away, perhaps eventually becoming too slow to produce radio emission and falling silent. If it's in a binary system, orbital evolution will gradually change the system's configuration, potentially shutting off or altering the emission mechanism. If it's a magneteer, the intense magnetic field that powers its activity might decay over thousands or millions of years, taking the radio emission with it. From the perspective of cosmic time, these scenarios unfold in mere moments. The universe is 13.8 billion years old. Stars have been forming and dying for over 13 billion years. Even if our signal source operates for millions of years before shutting off, that represents a tiny fraction of cosmic history. We happen to observe it during its active phase, but across the full span of galactic history, such objects might appear briefly, shine their peculiar light for a cosmically short time, then fade into quiescence. This raises a kind of cosmic anthropic consideration. We detect this signal because we exist now, with our current technology, looking at this particular patch of sky. In the universe's past, before radio astronomy existed, the signal went unnoticed despite reaching Earth with the same reliability. In the far future, perhaps the source will have fallen silent, or human civilization will have moved beyond such observations. We inhabit a particular moment in cosmic time when our capabilities align with the signal's existence. There's something both humbling and special about this intersection. Humbling because it emphasizes how our observations capture only a momentary slice of cosmic history, a brief window on processes that operated long before humans existed and will continue long after we're gone. Special because we happen to be here now, conscious beings capable of detecting and wondering about this cosmic broadcast, participating however briefly in the universe's ongoing story. The 44-minute signal, like all astronomical phenomena, ultimately reminds us of our cosmic context. We're pattern-recognizing intelligences that evolved on a planet orbiting an unremarkable star in the suburbs of a typical galaxy. Yet we've developed the ability to detect and analyze signals from cosmic sources our ancestors couldn't have imagined. We've built instruments that extend our senses across the electromagnetic spectrum and across cosmic distances, gathering light that travelled for eons to reach our detectors. This capability, this scientific understanding, represents one of humanity's great achievements, a triumph of curiosity and collaboration and patient observation. Each mystery we encounter, each signal we detect but don't yet fully understand, adds to both our knowledge and our appreciation for how much remains to be discovered. There's a philosophical perspective from which the 44-minute signal represents something profound beyond its physics, the universe becoming aware of itself through human consciousness and scientific inquiry. We are, in a very real sense, the universe examining its own operation, consciousness emerging from matter to contemplate matter's behaviour. This idea sounds mystical, but rests on straightforward facts. The atoms comprising your body, the calcium in your bones, the iron in your blood, the carbon chains of your DNA, all formed in the nuclear furnaces of ancient stars or in supernova explosions that scattered that processed material into space. You're quite literally made of stardust. Your substance created in stellar cores billions of years ago and cycled through multiple generations of stars before being incorporated into the cloud that formed our solar system 4.5 billion years ago. The same applies to everyone, to all life on Earth. Every living thing shares this cosmic ancestry. The oxygen you breathe was fused from helium in massive stars. The nitrogen in your proteins was synthesized in similar stellar processes. The very atoms comprising the molecules that make life possible spent billions of years drifting through interstellar space before gravity collected them into planets, where chemistry could elaborate them into the structures of biology. From this perspective, human consciousness represents a remarkable development in cosmic evolution. The universe, through a long chain of cause and effect, has created structures capable of understanding the rules that govern cosmic behaviour. Atoms organised into molecules, molecules into cells, cells into organisms, organisms into brains complex enough to model reality and predict future states based on present conditions and known laws. When astronomers detect the 44-minute signal, they're using instruments built from refined matter, electronics utilising quantum mechanical principles to amplify and process radio waves that travelled through space from their cosmic source. The signal, produced by processes involving extreme physics at the boundary of theoretical understanding, encounters Earth and human civilization at this particular moment, captured by arrays of antennas and analysed by computers executing algorithms designed by minds trying to comprehend what they observe. There's a loop here, a reflexive quality to the whole enterprise. Matter examining matter's behaviour, the universe studying itself through the medium of conscious beings who arose within it. The processes that created the 44-minute source, whatever they proved to be, operated according to the same fundamental physical laws that govern atomic physics, chemistry, biology, and ultimately neuroscience and cognition. This doesn't diminish the significance of human inquiry. If anything, it amplifies it. We're not outside observers peering at the universe from some external vantage point. We're participants, emergent phenomena within the cosmic system we're attempting to understand. Our questions about the universe are the universe asking questions about itself. Our discoveries are the universe discovering its own nature. Carl Sagan expressed this beautifully. The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. This isn't poetic exaggeration but literal truth. The contemplation of cosmic mysteries, the attempt to understand phenomena like the 44-minute signal, represents one of the universe's most remarkable features, the emergence of self-awareness. This perspective transforms how we might think about our cosmic significance. From one angle, humans seem insignificant, brief flickers of consciousness on a small planet orbiting an ordinary star in an unremarkable galaxy, among hundreds of billions of galaxies. We occupy a tiny fraction of space and time, our entire species' existence spanning perhaps a few 100,000 years out of cosmic history, stretching 13.8 billion years into the past and likely trillions or more years into the future. Yet from another angle, consciousness itself might be exceedingly rare and precious. If life is uncommon, if intelligence is improbable, if technological civilization represents an outcome achieved by only a tiny fraction of the planets where life emerges, then perhaps consciousness is among the universe's most valuable products. The ability to understand, to model, to predict, to create art and music and mathematics that describe reality. These might be extraordinarily special outcomes of cosmic evolution. We don't know how rare or common intelligent life is. The Fermi paradox captures this uncertainty. If the universe is vast and old, and if life is reasonably common, where is everybody? Why haven't we detected any definitive signs of other technological civilizations? This silence might mean intelligence is rare, or it might mean civilizations don't last long, or it might mean they're common, but communication across cosmic distances proves too difficult or uninteresting. The question remains open, adding another layer to our contemplation of signals like the 44-minute source. When we detect something unusual, part of our consideration necessarily includes whether it could be artificial, whether it might represent another instance of the universe becoming self-aware through the emergence of intelligence elsewhere. So far, every mysterious signal has proven natural, produced by astrophysical processes rather than conscious design. But the searching itself, the careful analysis to distinguish natural from artificial, represents something meaningful. We're looking for cosmic cousins, for other instances of matter organising itself into patterns capable of thought and communication. We're asking whether we're alone or part of a larger community of conscious beings scattered through space and time. This search, like the broader scientific enterprise, reflects deep human drives, curiosity about our origins and context, desire for connection, hope that consciousness extends beyond our single example. Fear perhaps that we might be alone bearing the burden of understanding without any others to share the wonder with. The 44-minute signal, natural though it likely is, participates in this larger story. It's a cosmic phenomenon we detect and attempt to understand using capabilities developed over generations of scientific work. It challenges us, resists immediate explanation, invites continued investigation. In doing so, it serves its role in the universe's ongoing project of self-discovery. Another puzzle piece in the infinite jigsaw of cosmic understanding that conscious minds gradually assemble. As we move into the quieter reaches of our exploration, into the space where thought and rest begin to blend, we can find a particular kind of beauty in the uncertainty surrounding the 44-minute signal. A peaceful acceptance that not all questions need immediate answers, and that mystery itself holds value worth cherishing. Western culture often treats uncertainty as uncomfortable, something to be eliminated through knowledge and control. We want answers, solutions, closure. The idea that a question might remain unresolved creates tension, a sense of incompleteness that we rush to fill with explanations even when evidence doesn't quite support them. But there's an alternative perspective, one that treats mystery as valuable in its own right, that finds peace in dwelling with questions rather than hastily grasping at answers. The Japanese aesthetic concept of wabi-sabi offers one framework for appreciating this perspective. Wabi-sabi finds beauty in imperfection, impermanence, and incompleteness. It suggests that flawed, incomplete, or uncertain states possess their own kind of beauty, perhaps deeper than the beauty of perfection or certainty. A partially glimpsed truth might be more evocative than a fully revealed one, leaving space for imagination and wonder. Applied to the 44-minute signal, this perspective allows us to appreciate it as it currently exists, a confirmed phenomenon with well-measured properties but uncertain origins. We know it's there, we know how it behaves, but we don't yet know why. This state of knowledge, partial but growing, represents a particular moment in the scientific process that has its own character and value. There's something genuinely beautiful about the signal itself as an observed phenomenon, independent of explanation. The precision of that 44-minute rhythm, maintained pulse after pulse across weeks and months of observation, exhibits a kind of cosmic choreography. Something out there in the galaxy is ticking like a clock, sending its radio message toward Earth with mechanical regularity, a rhythm playing out in the darkness of space whether anyone listens or not. The polarization of the radio waves suggests intense magnetic fields, curved and twisted in complex geometries. Picture those field lines, if you will, looping and spiraling around their source, channeling charged particles into beams that sweep across space. The physics creating this configuration involves energies and field strengths far beyond anything achievable in terrestrial laboratories. Matter and magnetism pushed to extremes that exist naturally only in the most exotic cosmic environments. The radio waves themselves, spreading outward from their source at the speed of light, carry information encoded in their properties. Each photon making up those waves was emitted by an accelerated charged particle, an electron perhaps, whipping around magnetic field lines at nearly the speed of light. That photon travelled through interstellar space, through regions of gas and dust, past other stars and their planets, until it arrived at Earth and happened to encounter one of our radio telescope antennas. Think about that journey, the path of a single photon across the galaxy. It might have travelled for decades or centuries, crossing light years of mostly empty space, but occasionally passing through denser regions where nebulae glow or young stars form. It survived the journey intact, maintaining its frequency and polarization, carrying its cargo of information about the source that created it. And then it reached Earth, at just the right time to be detected when our telescopes were listening, adding its tiny energy to the accumulated signal we measure. There's profound beauty in this cosmic intersection, this meeting of light and instrument across vast distances. The universe is creating these photons constantly, from countless sources, radio waves filling space in all directions, from every active radio source in the cosmos. Most pass through the solar system undetected, their information lost because no antenna happens to be positioned and oriented to catch them. But some, a vanishingly small fraction, encounter our telescopes and reveal their secrets. The uncertainty about the source's nature doesn't diminish this beauty. If anything, it enhances it. We're detecting something real and measurable, confirmed and studied, yet it retains an element of mystery that invites continued contemplation. Each new observation might bring revelation, or it might simply add another piece to the slowly accumulating puzzle. Either way, the process continues, patient and methodical, guided by curiosity and sustained by wonder. This acceptance of mystery as valuable connects to broader questions about meaning and satisfaction. Perhaps we don't always need definitive answers. Perhaps the journey toward understanding, the gradual accumulation of knowledge, the refinement of questions even when answers remain distant. Perhaps this process itself provides meaning and satisfaction independent of final conclusions. Scientists working on the 44-minute signal likely experience this in their daily work. They might not solve the mystery during their careers. They might contribute observations and analysis that help narrow possibilities without identifying the definitive answer. And yet the work remains meaningful, each small contribution adding to collective understanding. Each ruled-out possibility bringing the community marginally closer to truth. There's a lesson here about how to live with uncertainty in general, about finding peace with unanswered questions rather than letting them create anxiety. The universe contains far more that we don't understand than that we do. Every answered question seems to reveal multiple new questions waiting beneath. If we require complete understanding before we can feel settled, we'll never find peace. But if we can accept mystery as natural, as an inherent feature of existence rather than a temporary problem awaiting solution, then perhaps we can rest more easily. We can appreciate what we do know while acknowledging the vastness of what we don't, finding beauty in both the illuminated and the shadowed regions of understanding. The 44-minute signal reminds us that the universe likely contains many phenomena we haven't yet detected simply because we haven't developed the right instruments or learned to look in the right ways. The history of astronomy is full of such discoveries. Signals that were always there but invisible until technology advanced sufficiently to reveal them. Consider infrared astronomy, the study of heat radiation from cosmic sources. Throughout human history, countless infrared photons from space reached Earth's surface, but we couldn't see them because our eyes aren't sensitive to those wavelengths. The atmosphere absorbs most infrared radiation anyway, making ground-based infrared astronomy difficult until the development of cooled detectors and stratospheric or space-based observatories. The first infrared surveys of the sky in the 1960s and 70s revealed a universe invisible to optical telescopes. Cool objects too faint to shine in visible light blazed brightly in infrared. Dust-shrouded, star-forming regions, opaque to optical light, became transparent at longer wavelengths. Distant galaxies whose visible light had been redshifted into the infrared by cosmic expansion appeared for the first time. An entirely new view of the cosmos emerged once we gained infrared sight. Ultraviolet astronomy faced similar constraints. Earth's atmosphere blocks most ultraviolet radiation, protecting surface life from harmful UV rays, but preventing astronomical observations in those wavelengths. Only with satellite observatories like the International Ultraviolet Explorer and the Hubble Space Telescope could astronomers routinely study the UV universe, discovering hot stars, active galaxies, and energetic processes invisible at other wavelengths. X-ray astronomy was impossible before rocket and satellite technology allowed detectors to rise above the absorbing atmosphere. The Sun emits X-rays from its corona, but stellar X-ray emission remained unknown until the 1960s, when rocket flights detected X-rays from the Sun and a handful of other sources. Early X-ray observatories revealed neutron stars, black holes, hot gas in galaxy clusters, supernova remnants, phenomena that operate at temperatures of millions of degrees and emit most of their energy in X-ray wavelengths. Gravitational wave astronomy represents perhaps the ultimate example of signals that were always present but required extraordinary technology to detect. Einstein predicted gravitational waves in 1916, but the technology to detect them, interferometers with arm lengths of kilometers and sensitivity to length changes smaller than a proton's diameter, wasn't realized until LIGO achieved first light in the early 2000s and didn't detect actual gravitational waves until 2015. During all those decades between prediction and detection, gravitational waves were passing through Earth constantly. Merging black holes and neutron stars throughout the universe were creating ripples in space-time that propagated across cosmic distances, washing over our planet without any indication that we could perceive. The signals were there, we simply lacked the instruments to hear them. What else might we be missing? What phenomena exist in frequencies we haven't explored, at timescales we haven't monitored, in regions of space we haven't surveyed with sufficient sensitivity? The 44-minute signal existed for years at minimum, possibly decades or centuries before our telescopes happened to catch it. How many other similar sources pulse away undetected because we haven't conducted the right surveys yet? The universe might be full of neutrino sources that current detectors can't see. Neutrinos barely interact with matter. Trillions pass through your body every second from the sun alone without any effect. Only occasionally does one interact with atomic nuclei, creating detectable signals in carefully designed detectors. Current neutrino observatories detect solar neutrinos and occasional supernova neutrinos, plus a few cosmic neutrinos from active galactic nuclei and other sources, but we might be missing entire classes of neutrino-producing phenomena simply because our detectors aren't large enough or sensitive enough yet. Dark matter, comprising roughly 25% of the universe's total mass energy, remains undetected directly despite decades of searching. We know it exists from its gravitational effects on galaxies and galaxy clusters, but we don't know what particles comprise it. Perhaps dark matter interacts with itself or with ordinary matter in ways we haven't tested yet. Perhaps it creates subtle signals that we'd recognise if we knew what to look for, but that remain invisible to our current experimental approaches. There might be extremely long-period phenomena, astronomical events that unfold over centuries or millennia, that we'll never detect with certainty, because human astronomy has existed for only a few centuries, and modern instrumentation for just decades. Imagine a star that varies in brightness with a period of 1,000 years. During all of recorded history, it would have gone through perhaps 3 complete cycles. We might notice slow brightening or dimming if we compared observations separated by decades, but establishing the full period would require observations spanning longer than any scientific institution or even civilization has persisted. The cosmic microwave background contains information about the universe's first moments, patterns imprinted during inflation, and the subsequent evolution of primordial density perturbations. Current measurements resolve these patterns down to angular scales of a few arc-minutes. But smaller scale features might exist, information about physics at the earliest moments, that we can't detect because the foreground contamination from our galaxy and extragalactic sources becomes overwhelming at those small scales. Future instruments will undoubtedly reveal phenomena currently beyond our reach. The James Webb Space Telescope, launched in late 2021, already shows us the universe in infrared wavelengths with unprecedented clarity. Detecting the most distant galaxies ever observed, seeing through dust to watch stellar birth, examining exoplanet atmospheres with remarkable precision. Each new capability reveals new surprises, objects and phenomena theorists hadn't quite predicted. Next-generation extremely large telescopes with mirrors 30 or even 40 meters in diameter will detect even fainter objects and resolve finer details. Improved adaptive optics will compensate for atmospheric turbulence with increasing effectiveness. New detector technologies will capture light more efficiently across broader wavelength ranges. Each advance opens new parameter space for discovery. And beyond electromagnetic radiation, future gravitational wave observatories like LISA, planned for space deployment in the 2030s, will detect lower frequency gravitational waves than ground-based interferometers can access. These might reveal supermassive black hole mergers in distant galaxies, confirming how these billion solar mass monsters formed and evolved across cosmic history. The 44-minute signal represents one discovery in this ongoing process of expanding our sensory reach into the cosmos, learning to detect signals that were always present but previously invisible. It reminds us that the universe still holds secrets, that our current understanding, while substantial, remains incomplete, and that future observations will certainly surprise us with phenomena we haven't yet imagined. Scientific discovery often follows rhythms much slower than popular culture suggests, with breakthroughs emerging not in sudden flashes of insight, but through gradual accumulation of evidence and slow refinement of understanding. The story of the 44-minute signal illustrates these patient rhythms, the careful, methodical work that characterizes modern science. The initial detection came from systematic survey work, astronomers methodically mapping the radio sky night after night, accumulating vast catalogues of sources. This kind of work lacks dramatic appeal. There's no single moment of discovery, just the slow build-up of data until anomalies emerge from automated analysis. Yet it's this systematic approach that enables most modern astronomical discoveries, creating datasets comprehensive enough that rare and unusual objects appear among the thousands or millions of ordinary sources. Following detection, confirmation requires repeated observations over extended periods. You need to verify that the signal persists, that it wasn't a transient glitch or interference. You need to measure properties accurately, which requires multiple observations under varying conditions. You need to check whether the signal appears in different telescope systems, ruling out instrumental artifacts. This process takes months minimum, often years, each observation adding confidence that the phenomenon is real. Theoretical work proceeds on similar timescales. Initial papers might propose several possible explanations, each with supporting arguments and problematic aspects. Other researchers examine these proposals, developing detailed models, making predictions that can be tested by further observations. Debate occurs through journal publications and conference presentations, the community gradually converging toward more plausible explanations while ruling out others. This back and forth between observation and theory, each informing the other, creates a slow, oscillating approach toward truth. Observations constrain theoretical models showing which are consistent with reality, and which make predictions that observations contradict. Models guide observations, suggesting what measurements would most effectively distinguish between competing explanations. Neither proceeds entirely independently, they co-evolve, each driving refinement in the other. the pace can feel frustratingly slow to those outside the process. Why can't scientists just solve this immediately? Why the uncertainty and careful hedging? But this deliberation is a feature, not a bug. Science values getting the right answer over getting a quick answer. Premature conclusions made before evidence is sufficient often turn out wrong and must later be retracted, creating confusion and undermining public trust in scientific conclusions. History provides numerous examples of discoveries that required decades or longer to fully understand. Pulsars were discovered in 1967, but the details of how they generate their radio emission remain debated for years. Only gradually, through accumulated observations and theoretical refinement, did the current consensus picture emerge. Rapidly rotating neutron stars with intense magnetic fields channeling radiation into beams that sweep across space. Even now, some details remain uncertain. Quasars, discovered as radio sources with peculiar optical spectra in the early 1960s, generated intense controversy about their nature and distance. Some astronomers argued they must be relatively nearby objects in our galaxy to explain their brightness. Others proposed they were extremely distant and incredibly luminous. The debate persisted for years until better observations and theoretical work confirmed the latter explanation. Quasars are powered by supermassive black holes in distant galaxy cores. Their enormous luminosity explained by efficient conversion of gravitational potential energy into radiation as matter falls toward the black hole. The nature of gamma-ray bursts remained mysterious for decades after their discovery. Early detections showed only that they came from random directions and released enormous energy in gamma rays. But distance remained unknown. Were they in our solar system? Our galaxy? The distant universe? Only in the late 1990s did observations of optical afterglows finally pin down distances, revealing that gamma-ray bursts came from galaxies billions of light-years away, making them the most energetic explosions in the universe since the Big Bang. Each of these examples illustrates the same pattern. Initial detection, years or decades of uncertainty and debate. Gradual convergence toward correct explanation as evidence accumulates and theoretical models improve. The 44-minute signal likely follows a similar trajectory. The initial detection has occurred, confirmation is underway, theoretical proposals have been made. Now comes the slow work of gathering more data, testing predictions, ruling out possibilities, narrowing the field until eventually, perhaps years from now, consensus emerges. This slow rhythm connects to larger patterns in how knowledge accumulates. Scientific understanding builds incrementally, each generation adding to foundations laid by previous ones. Individuals contribute pieces, sometimes large discoveries, more often small refinements, all of which aggregate into collective knowledge that no single person could achieve alone. There's profound satisfaction in being part of this process even when individual contributions seem small. The astronomer who observed the 44-minute source for 3 nights, gathering photons and measuring flux densities, might not solve the mystery alone. But those observations become part of the dataset others will analyse. The theorist who developed a model that didn't quite work still contributed by demonstrating what the answer isn't, narrowing possibilities for those who come after. Science as a collective enterprise operates on generational timescales. The questions one generation raises might be answered by the next or the one after that. The instruments one era builds enable the discoveries of future eras. The students trained today will train the next generation, who will train the one after that, knowledge and methodology passing forward through time like a relay race, where no single runner completes the course, but the baton continues moving. This long view provides perspective that can make contemporary frustrations more bearable. Of course, we don't understand everything yet. Of course, mysteries persist. The universe has been revealing its secrets to human inquiry for only a few centuries of systematic science, a cosmic eye blink. We've barely begun the work of understanding. As we drift closer to the edge of sleep, Into that liminal space where thought becomes dreamlike and boundaries blur, we can contemplate where wonder truly lives, not in complete understanding, but in the very process of reaching toward it, in the questions we ask and the mysteries we encounter. Wonder emerges from the contact between known and unknown, the boundary where our understanding meets what we don't yet comprehend. It's the feeling that arises when we recognize both what we know and the vastness of what we don't, when we perceive patterns and order emerging from apparent chaos, when we detect signals from across cosmic distances and attempt to interpret their meaning. The 44-minute signal creates wonder not despite its mystery, but because of it. If we immediately understood its source and mechanism, it might be interesting, a new data point in our catalogue of cosmic phenomena, but it wouldn't carry the same sense of profound puzzle. The uncertainty, the way it sits just beyond current explanation, invites contemplation and imagination. What could create such a signal? What physics operates at its source? What would we see if we could visit it directly? This wondering, this questioning curiosity seems fundamental to consciousness itself. Other animals navigate their environments with skill, adapting to conditions, learning from experience. But humans, and perhaps a few other species, seem to wonder in a deeper sense, to ask why, questions that go beyond immediate practical concerns. We want to understand not just how to survive, but how things work, what causes what patterns govern events. Children embody this wondering naturally. They ask endless questions. Why is the sky blue? Where does the sun go at night? How many stars are there? Driven by genuine curiosity rather than practical need. Something in the human mind seeks understanding and pattern, finds satisfaction in explanation, and deeper dissatisfaction when questions remain unanswered. Science channels this wondering into systematic investigation, developing methods for testing ideas and distinguishing truth from falsehood. But the emotional core of scientific inquiry, the driving motivation, remains wonder. Scientists study cosmic mysteries not just for practical applications or career advancement, but because they genuinely want to know, because the universe fascinates them and understanding feels meaningful. The 44-minute signal touches this sense of wonder across multiple dimensions. There's wonder at the precision of the timing, that anything in the chaotic universe could maintain such regularity. There's wonder at the vast distances involved, that we can detect and measure signals from cosmic sources light years away. There's wonder at the physics required to produce the emission, extreme conditions of density and magnetic field strength that don't exist anywhere in human experience. There's also deeper wonder at the fact that we can detect and study such phenomena at all, that matter organised into biological forms, into nervous systems and brains, could develop the capability to build radio telescopes and analyse electromagnetic radiation, to develop mathematical models and test them against observations, to gradually piece together an understanding of cosmic processes. All of this seems improbable and remarkable. The universe might have been different. Physical laws might have precluded the formation of complex structures. Chemistry might have been too simple to support biology. Evolution might not have favoured intelligence. Conscious minds might never have emerged to wonder about cosmic signals. But here we are, awareness contemplating the cosmos, using instruments built from refined matter to detect other matter's behaviour across vast distances. This situation itself deserves wonder. The universe has become self-aware through the emergence of conscious beings who study and model and predict. The radio waves from the 44-minute source travel through space according to Maxwell's equations of electromagnetism, arrive at Earth, encounter radio telescopes built using principles of quantum mechanics and solid-state physics, get converted to electrical signals and processed by computers running algorithms designed by minds trying to understand what they observe. Each step of this process depends on the same underlying physics. From the emission mechanism at the source to the neural activity in astronomers' brains as they contemplate the data, It's all connected, all part of the same cosmic system, operating according to consistent physical laws. We're not outside observers but participants, matter studying matter, the universe examining itself through the lens of consciousness that emerged from its own processes. This recursive quality, this loop of self-reference, might be the deepest source of wonder. Not just that the universe exists, not just that it follows mathematical patterns we can discover, but that it contains within itself structures capable of understanding those patterns, minds that can model the system they're embedded in, and make predictions that observations confirm. The 44-minute signal participates in this larger dance. Its source, whatever it is, operates according to physical principles we've partially grasped. The signal itself propagates through space following well-understood rules of electromagnetic wave propagation. Our detection and analysis employ instruments and techniques developed through decades of accumulated knowledge. Our attempts at explanation draw on theoretical frameworks built across generations of scientific work. And yet mystery remains, gaps in understanding, questions not yet answered. This combination, partial. Before I say goodnight, I want you to know something. You just spent 2.5 hours inside the mystery of the 44-minute signal. Most people scrolled past this video tonight. You didn't. And if this quiet corner of the universe is somewhere you want to return to, a like and subscribe makes sure you always find your way back and help someone else who needs this find it too. Now, let's rest. This combination, partial knowledge alongside persisting mystery, creates the conditions for wonder to flourish. We know enough to ask meaningful questions, but not enough to answer them completely. We stand at the boundary between known and unknown, reaching toward understanding. This is where wonder lives, not in complete ignorance, which provides nothing to wonder about, and not in complete knowledge, which leaves nothing to question, but in the productive space between, where questions emerge from partial understanding and drive us toward deeper comprehension. In these final moments before we part, before sleep claims those ready to drift away, we can hold one last image in our minds, a thought to carry into rest or into the quiet continuation of the night. Somewhere out there in the galaxy, right now as you listen to these words, the source of the 44-minute signal is ticking through another cycle. Perhaps it just completed a pulse, sending radio waves streaming outward into space in all directions. Perhaps it's in its quiet phase, the dark period between emissions, gathering energy, or simply following whatever physical process governs its periodic behaviour. The radio waves from that source are travelling outward at the speed of light, 300,000 kilometres per second, crossing interstellar distances. Some of those waves, a vanishingly small fraction, are aimed toward Earth, making the journey that will end with their detection by our radio telescope sometime in the future. The waves that our instruments detected when the signal was first discovered began their journey years or decades ago, crossing the distance between the source and our planet while human civilization went about its business. Unaware that radio photons were en route carrying information about a mysterious cosmic object. This process continues whether we observe it or not. The source doesn't pulse for our benefit, doesn't aim its emissions toward Earth deliberately. It simply operates according to whatever physics governs its behaviour, cycling through its 44-minute rhythm as it has for however long it's existed and will continue to do for however long its energy reserves and physical stability persist. There's something peaceful about this indifference, this continuing natural process that unfolds independent of human attention. The universe operates according to its own rhythms, vast and patient, on timescales that dwarf human concerns. Whether we understand the 44-minute source or not, whether we solve the mystery in our lifetimes or leave it for future generations, the signal will likely continue, pulsing its radio message into the darkness. Other signals pulse as well. Throughout the cosmos, thousands of known pulsars rotate at their various rates, from millisecond pulsars spinning hundreds of times per second to slower ones ticking every few seconds. Eclipsing binary stars orbit each other, creating brightness variations as they periodically pass in front of one another. Variable stars swell and contract, breathing in and out over days or weeks or months. Supermassive black hole binaries spiral together over millions of years, gradually drawing closer as they radiate gravitational waves. All of these cosmic clocks tick simultaneously, creating overlapping rhythms at every timescale from fractions of seconds to eons. Some we've detected and catalogued. Others remain unknown, their signals either too faint for our current instruments, or in frequencies we haven't explored, or with periods we haven't monitored long enough to recognise. The radio sky is filled with these various signals, a symphony of electromagnetic radiation at different frequencies, some continuous, some periodic, some sporadic. Every point in space receives radio waves from countless sources, all mixed together, creating a complex pattern that requires sophisticated instruments and careful analysis to separate and understand. Earth sits in this bath of cosmic radio waves, receiving signals that began their journeys from sources ranging from a few light seconds away for solar system objects to billions of light years distant for the most remote galaxies and quasars. We've learned to listen selectively, tuning our radio telescopes to specific frequencies and directions, filtering out the noise to detect and study individual sources. The 44-minute signal is one voice in this cosmic chorus, distinctive in its regular rhythm and unusual period, mysterious in its unknown nature, but fundamentally part of the natural electromagnetic environment the universe creates. In years to come, we'll likely understand it better. Perhaps someone reading this years from now will know the answer, will understand what object produces that precise 44-minute pulse and why. But even when the mystery is solved, even when we understand the physics and can explain the emission mechanism with confidence, the signal itself will remain what it's always been, a natural phenomenon, a periodic broadcast from somewhere in our galaxy, radio waves travelling through space at light speed, carrying information encoded in their properties about the extreme conditions at their source. There's a kind of eternity in this continuity. Long before humans evolved, before Earth formed, stars were being born and dying. Neutron stars were forming and spinning and emitting radio waves that travelled through the galaxy, with no one to detect them. The universe was full of these signals, messages without recipients, information without observers. And in the far future, long after human civilization has either transformed beyond recognition or disappeared entirely, cosmic radio sources will likely continue pulsing and emitting, their signals propagating through space whether consciousness exists to detect them or not. We happen to exist now, in this brief window of cosmic time, with the capability to detect and wonder about these signals. It's a privileged position in a way, this moment of awareness and inquiry. We can listen to the universe's radio whispers and attempt to decode their meaning. We can build instruments that extend our senses across impossible distances and frequencies our bodies cannot perceive. We can develop theories and test them against observations, gradually piecing together an understanding of the cosmos we inhabit. The 44-minute signal invites us into this process. It presents a puzzle, genuine and well documented, neither too difficult to be completely intractable, nor so simple that it yields immediately to analysis. It sits at that productive boundary where current knowledge can make progress, but hasn't yet reached definitive conclusions. It will likely be solved, given time and effort and technological advances. But that solution lies somewhere in the future, requiring patience and continued observation. Until then, the signal pulses on, keeping its mysterious rhythm, sending its radio message that travels through space at the speed of the light, occasionally intercepted by Earth's radio telescopes and recorded for analysis by curious minds wondering what it means and where it comes from, and what it tells us about the universe we're part of. As we prepare to part ways, as those ready for sleep begin to drift and those remaining awake settle into the quiet of late night, we can hold this image somewhere in the galaxy, separated from us by hundreds or thousands of light years of space. An unknown source ticks through another cycle of its 44-minute rhythm, operating according to physics we partially understand, creating radio waves that will travel for years or decades before reaching Earth, carrying information about processes at the boundary of our current knowledge, another cosmic mystery waiting patiently to be solved. We've travelled together through this long night, exploring a cosmic mystery that began with a simple observation. A repeated signal with a period of 44 minutes, detected by radio telescopes in Australia and confirmed through follow-up observations. Thank you for staying with me through this entire journey. These 2.5 hours we've spent contemplating what this signal might be, and what it tells us about the universe and our attempts to understand it. From the initial discovery to the hunt for identity, from the search for similar sources to the theoretical explanations proposed, from the philosophical implications to the peaceful acceptance of mystery. We've covered the landscape of what this signal represents both scientifically and more broadly in terms of human inquiry and wonder. The answer, as honestly as I can give it, is that we don't yet know exactly what creates the 44-minute signal. The evidence points towards some kind of stellar remnant, most likely a neutron star in an unusual state or configuration that current models haven't quite captured. It might be a long-period magnetar, a type of object that hasn't been definitively observed before. It might represent a transition state in neutron star evolution that we've been fortunate enough to catch during its active phase. Or it might be something else entirely, a phenomenon at the boundary of our understanding that will require new theoretical work to fully explain. But perhaps what matters most isn't the final answer whenever it comes, but the journey toward it. The careful observations, the rigorous analysis, the theoretical creativity, the patient accumulation of evidence, the honest acknowledgement of uncertainty. All of this represents science at its best, driven by curiosity and wonder, proceeding methodically toward truth even when that truth remains distant. If you enjoyed this slow drift through cosmic mystery, a like and subscribe really helps reach others seeking the same peaceful way to end their day. These explorations take time to research and craft, balancing scientific accuracy with the calm delivery needed for sleep content. Your support makes them possible. And to those already subscribed, thank you for being here, for trusting these journeys into astronomical puzzles and cosmic questions. Feel free to leave a comment sharing where in the world you're watching from. What aspects of this mystery most intrigued you, or what other cosmic topics you'd like to explore in future videos? I read every comment, and your thoughts and suggestions genuinely shape what we explore together. Wherever you are in the world right now, whether you're lying in a comfortable bed in darkness or sitting in a quiet corner as the night deepens, I hope your breathing has slowed and steadied over these past 2.5 hours. I hope your thoughts have quieted, your body feels heavy and warm, your mind has found a kind of peace in contemplating cosmic mysteries that exist independent of daily worries and concerns. Look up at the stars tonight, if you can, if the sky is clear and you can see them through whatever windows or circumstances surround you. Or imagine them if you can't, that vast field of distant suns scattered across the darkness, each one potentially hosting planets and perhaps life, each one representing a world of possibilities and mysteries. Somewhere among those stars, separated from us by distance measured in light years, an unknown source is pulsing with a period of 44 minutes, sending radio waves streaming into space. Those waves travel at the speed of light through the near vacuum of interstellar space, passing through clouds of gas and dust, threading between other stars and their planetary systems, covering vast distances with patient inevitability. Some of those radio waves are aimed toward Earth, making the long journey across the galaxy, carrying information about their source encoded in properties we can measure and analyze. They might arrive days or years or decades from now, depending on how far away the source is located. When they do arrive, our radio telescopes might be listening, might catch those photons and convert them to electrical signals, and add them to our growing data set about this mysterious source. All those radio waves travelling through space, all those cosmic signals arriving at Earth from countless sources, all the phenomena we've discovered and all those still waiting to be detected, all of this is part of the universe's ongoing story, a story we participate in through our observations and attempts at understanding. In the end, what we're left with is not just a mystery about a particular radio source, but a deeper appreciation for the process of discovery itself, for the patience required to work on problems that might not be solved quickly, for the beauty in questions as much as in answers, for the wonder that emerges when we contemplate how much the universe still has to teach us. The 44-minute signal will likely be explained eventually. Future observations will constrain the possibilities further. New instruments will provide capabilities current telescopes lack. Theoretical models will be refined and tested. Gradually the mystery will yield to understanding, and we'll add this phenomenon to our catalogue of known cosmic processes, one more piece fitted into the vast puzzle of how the universe operates. But for now, tonight, as sleep approaches or the quiet hours stretch ahead, we can rest in the knowledge that mysteries exist, that the universe still surprises us, that there are rhythms and patterns out there in the darkness ticking away patiently, waiting to be discovered and understood and appreciated. Sleep well, wherever you are. Dream of cosmic signals travelling through space at light speed. Dream of radio telescopes listening to the electromagnetic whispers of distant objects. Dream of mysteries solved and mysteries yet to be encountered. Dream of the universe continuing its patient unfolding, governed by physical laws we're gradually learning to comprehend. And when you wake, the signal will still be there, pulsing every 44 minutes, sending its message into the void, a cosmic mystery that connects us to the larger universe we inhabit, and to the ongoing human project of trying to understand it. Good night. Thank you for this journey. Until next time, may your rest be deep, your dreams peaceful, and your wonder at the cosmos remain bright.